The Electronic Alliance brings you another in a series of technical presentations continuing to educate you in product design and manufacturing. Today's session is about RF design basics and pitfalls. We welcome Farron Dacus of Longwing Technology. Anytime you need to find a qualified source for your design and manufacturing needs, contact the Electronics Alliance.
Hello everybody. Well, very glad to see we have such an interested group of people here today. A lot of interest in radio these days, somewhat differently from the past. I remember once I went to take my first graduate class in RF circuit design over at UT Arlington, and the class didn't make. 3 guys showed up for the class, and that was 1986, and since then, you know, radio's gotten a lot bigger. Okay, so here's what we'll be covering today. We're going to go through some of the CAD methods, which these days are a lot more convenient than in the past. You can get very good, you know, low-cost PC software for doing RF simulation these days. And then I'm going to try to do kind of a top-down presentation, progressing, starting with old-fashioned RF, which is mostly circuit design oriented, and then coming into the system design and top-down there, explain why system design is so important these days. But, you know, basically, you know, when you hold your cell phone these days, it's like you got all of electronics engineering in your hand, because you have not just radio, but a very complicated system design, a lot of software, complicated power systems. It's there's a lot of complexity in wireless systems today. Okay, so specialized analysis. Used to be that, you know, when I first got into RF, it was basically just a specialty within analog circuit design. But since then, it's gotten to be, you know, much more involved with the system design, the software, and the digital signal processing. So I'll try to get a flavor of all of that across today. Of course, you know, it's a master's degree and a career to really be expert in it, but it's surprising what you can pick up in just a brief time, you know, if you try to just highlight the important point. So, starting with the CAD, RF circuit design is typically done with a kind of circuit parameter they call S parameters or scattering parameters. And, you know, they're similar in concept to what is taught, you know, at the sophomore level with like H parameters and Y parameters, except instead of voltage and current, it's forward and reflected waves. And this is kind of a Hewlett-Packard innovation to develop and promote this, and it's what's measured on network analyzers. And the reason that is done is because at true RF frequencies, there's no such thing as a real open or short. There's some typical numbers given on screen here, but a 1 nanohenry inductance, which is typical of a lead on a component, a tiny component, it will be about 6 ohms at a gigahertz, and a puff of capacitance, which is typical of a small surface mount part to its ground plane, will be about 160 ohms. Now, as an example of some of the specialized techniques needed in RF circuit design, is the fact that parts are more complicated than they are at low frequency. You have to take their parasitics into account, and for a capacitor, here is the, you know, intended capacitance, and it has a Q limiting resistance, and what really trips you up is the series inductance. So this capacitance will have a series mode self-resonance, and if we do a few simple calculations, we can find that below its self-resonance, which is this zone right here, below that critical frequency, it has an effective capacitance which appears larger than the rated capacitance, due to the fact that as you approach this series self-resonance, the impedance approaches 0, or this Q limiting resistance, which makes the capacitance appear larger in generating the low impedance. So that leads kind of straight into a trick that's nice to be aware of. There's many of these, of course, in RF, but, you know, this is one that follows directly from some of these basic principles, and is quite handy when you're having to handle some real RF power, which is this. High-quality RF caps will typically show, as it says there, a smaller Q with larger capacitance, generally about half the Q with twice the capacitance. So if you parallel two caps with smaller value, you can get a much higher Q than the large larger capacitance. So generally, you can maintain the Q of the smaller capacitance when you parallel up copies of it. Now, why would you care about that? Well, if you get into any RF power levels above, say, about 1 watt, you'll find that it's very easy to exceed the power rating of, say, 0402 cap. You can avoid buying much more expensive capacitors, like porcelain microwave capacitors, by paralleling up a couple of low-cost COG capacitors. And often you can outperform that more expensive capacitor, as well. Okay, microphonics. This is another capacitor issue. High dielectric constant capacitors, these X5R, X7R, and Y5V capacitors have been, a real help in electronic design because they put a lot of capacitance into a small package. So they have attained a whole lot of popularity. Their problem in some spots in RF design is that they're piezoelectric. And in RF, you often can't tolerate the noise. I'll talk a little bit about some noise issues later, but the reason noise is so important in RF basically comes down to dynamic range. You take a 1 watt transmitter and you try and get some range out of it down to, say, a receiver sensitivity level, which for low data rates might be minus 120 dBm. That is a 150 dB dynamic range. So allowing that dynamic range means that you typically have to work down to the noise floor, and I mean the thermal noise floor. You don't want a lot of other things degrading that noise floor, and in a high vibration environment, say on an aircraft, that can easily happen, that the jet turbine vibration will shake these capacitors and generate a lot of noise at the turbine spin rate. And so you have to be real careful in the usage of those kinds of capacitors, and in particular in frequency synthesizers. You tend to hang quite a bit of capacitance a lot of times on, say, voltage control oscillator power inputs, because there's noise on those supplies that will tend to degrade the VCO, and a natural tendency is to put a little RC filtering right on that VCO supply line. But if you're shaking the capacitor in the RC, if you've got a 1 mic X7R cap hanging there, you might find that generates tens of dBs of visible noise on that VCO. So the answer there is use low noise supplies to start with, actively low noise, and then use these COG type caps when you can get away with the small capacitance. When you need more capacitance, go to tantalum or film. Don't go to the high dielectric solids. Okay, now let's look similarly in inductors. As I said before, capacitors typically show a series mode self-resonance. Inductors are the opposite. They tend to show a parallel mode self-resonance. So if we look at their impedance over frequency, at low frequency it's going up with inductance just like you'd expect, J omega L, but then it starts accelerating above that linear line, reaches a peak, self-resonant peak, and starts coming down. Well, we can do some simple math again to show that effective inductance is once again larger than the rated inductance, and that's something that has to be taken into account in anything where you're using a signal inductor, not a choke, but a signal inductor for filtering, for a tank in a VCO, anything like that. These things have to go in your simulator. An S-parameter simulator may let you put in self-resonance or Q directly, and it'll run that model internally. But if you're using, say, SPICE, then you have to put that exact model in, or even something a little more sophisticated for some parts. So here's an example. It's kind of hard to see, but I've got a low-pass LC filter here. Here's the intended parallel capacitors, and then series inductance. And it's got the Parasitics inserted for those parts, and then here is our low-pass function. But as we get out here where these parts start to go self-resonant, we see all these saw teeth form in the pattern. Instead of the transfer function continuing to go down, it reaches these minimums and then bounces up and down. And this is something to be aware of, and even a very simple LC filter, you'll get this floor of attenuation of the filter. It doesn't just keep going down. So the bottom line there is you of course have to be aware of it and simulate it, and sometimes you need to use extra filter stages that you wouldn't have guessed going in because of that floor. Okay, the Smith chart. Not a lot of time to get into tremendous detail on this, but this is a very common circuit design tool that basically represents reflection coefficient, which naturally has a magnitude and a phase angle. So to keep in mind on the Smith chart, it's normally got these odd looking lines and circles. It's filled up with those when you see one, and it kind of hides the fact that there's some regions here that are very helpful to keep in mind. So the center of the Smith chart is normally 50 ohms. That could be something different. 50 ohms is standard practice. Below that center is representing the reflections of coefficients that occur when you terminate a 50 ohm line with something capacitive. Above the line, inductive. Left of center, low impedance. Right of center, high impedance. And here's an example of how that is used. Got here a bipolar amplifier, which is set up here with the R's are in a feedback bias scheme that kind of counters the variable beta of the transistor, hard grounded emitter, common practice to help keep things stable. And looking into this amplifier, if we were to put it on a network analyzer and look right here, look this way, we see this impedance, which is typically capacitive, and for signal amplifiers often above 50 ohms, and we want to move that impedance to where it's pretty close to a 50 ohm match. And this shunt capacitor moves the impedance down further into the capacitive zone, and then a series inductor moves it back up toward the center. Often you can get away with just 2 matching elements to do a match like that. 3 is more flexible. You can match just about anything with 3 elements. Okay, so some layout rules for RF. Just like with the parts, they've got all those parasitics. Layout also has some special things to be aware of in RF design. So generally, to keep down a series inductance and the need to use transmission lines on the board, what we call strip lines, one part should flow right into the next. When you're using multiple decoupling capacitors to ground, which is a common practice because one may not have enough capacitance and it's got its own self-resonant problem, so you very often use a set of, say, power supply bypass caps. You normally put the smaller one right close to the sensitive node, and then the larger caps you'll work out, a little farther away. Magnetic coupling loops in RF layouts are a real problem. Let me give 2 examples. It's very easy to have instability in an RF amplifier. You get feedback from output to input that exceeds a magnitude of 1, and that amplifier starts acting like an oscillator. Just starts singing at some tone. And one of the ways you get that is through magnetic coupling loops with mutual inductance. So this is something that can be simulated. It can also be visualized, and if you can see where your current loops are, you can actually approximately calculate these things and see what is the coupling through this transformer mechanism that's set up by single loops in the layout, and how can that lead to instability. Another place I've seen these magnetic coupling loops cause a real problem is coupling in the noise of, say, switching power supplies. Everybody's gone to switching power supplies these days, but in RF it's a very bad idea to run sensitive RF circuits straight off a switcher, so there's usually at least one intermediate stage of linear regulation, and often 2. So you may be surprised sometimes when you set up, say, a switching power supply, and then you have 2 regulators following this thing. You think you've done your homework and that's going to be a real clean supply. You look at the spec on the linear regulator and it says you've got 55 dB of suppression at the switching frequency, so you're thinking, okay, I'm going to be 110 dB down on the switching noise on that supply to a sensitive point. Then you look at it and whoa, it's 40 dB down and not 110. And that is usually because of this magnetic coupling loop that's not in your simulation. You've done a good SPICE simulation in every regard except that magnetic coupling loop. Ground planes. Good ground plane methodology is something I have heard argued about my entire career in RF. And among experienced guys, it seems like it runs about 2 to 1 in favor of having one common ground plane. And that is the strategy that I usually adopt myself. I think in the cases where you see isolated ground planes tending to be lower noise, it's because that isolated ground plane interrupts some other problem you should have avoided, like magnetic coupling loops. If you didn't have that coupling loop in there, then the one ground plane would have been better. That's some of the typical black magic stuff in RF, but it's not really if you're just aware of the basic physics that's in place that leads to those layout rules.
I have a question about the ground plane.
Yeah.
Ground plane thing. When you say one ground plane, do you mean one ground plane on one layer? Or does that statement hold to maybe a second layer that has the same, is that the same potential, the same ground? Do you mean one layer, or do you mean...
I mean one layer, though it's not at all uncommon that you might have segments of ground plane on other layers for different purposes. For example, you can make a pretty good transmission line on a circuit board, called microstrip, by having a line of a certain width above a ground plane of a certain distance below it with a certain dielectric constant in the middle. And the ground plane you're using for the whole board might not be the one that's appropriate for a certain impedance you want. Like suppose you've got a couple of amplifiers that by their nature are closer to 100 ohms than 50 ohms output. And instead of wasting parts converting them to 50 ohms, maybe you want to run a piece of 100 ohm microstrip at a different distance, different depth from a ground plane you've set up for nominally 50 ohms in other places. So there are occasions when in this layout you would use other segments of ground plane, though in general the practice is you're going to set up one ground plane everywhere, including your digital section, though you're going to distance that off from an RF section. That is going to be set up for 50 ohm microstrip.
Could you explain more about the length and the coupling?
In sophomore level network theory, they usually introduce this concept of mutual inductance. So, an ideal inductor will have a coupling coefficient, usually use the letter K for this, of 1, and then as you get these loops farther apart, they couple less and less, or their mutual inductance is going down, and they're not transferring as much energy via magnetic field. But in RF here, we're looking for stuff that's perfectly isolated. So you might be surprised that, for example, you have a switching power supply, and you bring it near some sensitive circuitry. Then you put a linear regulator. And on the other side of that linear regulator, you have your sensitive circuitry. So there is a loop parallel to the ground plane where current flows, a current loop. And then over on the output side of the linear, there's another current loop. Well, these current loops are generating magnetic field, which comes up, off the board. Like if the surface of this table is the board, it's coming up off the board, looping around and coming back in, according to Faraday's law. And that magnetic field comes through the other loop. And there is a coupling coefficient between them. It's usually pretty small, but even if it's 0.001, when you're looking for 100 plus dB of isolation, it becomes almost a shorting factor. Energy goes through it, and you see the switching noise in the linear regulator output. So it is analytic. I mean, I could devote about a 1 hour long presentation to that and go through how you use Faraday's law and some simple integration to approximate, this problem. And the answer to it is you generally want shielding in between, and cheap plated steel is a pretty good shield, better than some of the more expensive shielding materials for that particular problem. And then the only other thing you can do is distance. You got to figure out how much isolation you need and separate those loops enough that that problem doesn't occur. Okay, key transceiver concepts. This guy named Edwin Armstrong invented the very first good receiver before World War I. It was called a regenerative receiver. And then he decided that wasn't good enough, and he invented the follow-on, the superheterodyne receiver. And that's still with us today. Now, the reason this thing works so great that it's lasted 100 years and no end in sight is because of what I mentioned earlier. There's a lot of dynamic range in radio communications systems. So you're generally looking to get right down to the noise floor. And getting down to the noise floor means you need excellent filtering. So if you've got, say, a voice signal consuming 10 kilohertz of bandwidth, you want to put surgical filtering around that signal and not introduce other noise, because noise is proportional to bandwidth. And it's amazing to me, but true, that most engineers have forgotten this. If they're not RF engineers, they've seen that in one lecture, it's never mentioned again, but that is like one of the most dominant things in RF, is that noise is proportional to bandwidth, and so you're always fighting to get noise bandwidth, as low as possible. And that's what a Superhet does. It does it two ways. First off, it converts the incoming signal to a fixed frequency where you can use an extremely good filter, a ceramic filter or a crystal filter historically, though these days it's often a low IF filter on die or digital signal filtering. But in addition to it being some type of physical process that allows narrow bandwidth because it's fixed, it's also converted down to a lower frequency. And at a lower frequency, for any given Q, the bandwidth is proportional to frequency. And so that lets you get that bandwidth down. Another related concept is the frequency synthesizer principle. Back in the 1880s, I forget who discovered this, but somebody figured out that a rock of quartz is an extremely high Q resonator. And we made crystal oscillators out of this for years, and if any of you were amateur radio operators in your youth, I remember back in the 70s you'd buy crystals and plug them in a radio, and you had single channel radio of good quality. These days you have this thing called the frequency synthesizer, which is a feedback control system that takes a voltage control oscillator, divides its frequency down, compares that to a crystal frequency, and then through a feedback mechanism adjusts the voltage controlled oscillator to be a precise multiple of the crystal. Put all that under computer control, combine it with the Superhet principle, and now you got a modern radio with wideband, can hit a bunch of different channels, and has got super good sensitivity. Okay, so here's an example of a modern transceiver, and it's got these an LNA to boost the signal without adding very much noise, then a mixer to down convert. You got an LNA ahead of the mixer because this mixer's got quite a bit of noise. You put some gain ahead of it, you overcome that. An IF filter, and then baseband processing. You got a synthesizer, which is normally shared with a transmitter chain, which does the opposite. You got some modulation at baseband, you up convert it, you filter it off to clean it up, you put as much gain as you want it, you drive the antenna, you got a switch to go between transmit and receive. And that's basically any modern transceiver. It's pretty much following this pattern.
Syntec is boasting a transceiver chip that claims to have receive sensitivity on the order of minus 140 dBm.
Possible.
150, approaching the theoretical noise floor possible.
Well,
and how effective can that be?
As long as I've been in the game, everybody's been able to design radios which approach the theoretical noise floor, within, say, 6 or 7 dB. You can design a receiver that can get, have a 6 dB noise figure. Now then, there's two ways that can improve this capability seemingly when people say they're going to the theoretical floor. One is that you need a certain amount of signal-to-noise ratio to demodulate. Now it's typically 10 or 11 dB. But through error correction, there's modern error correction techniques that reduce that quite a bit. Maybe 4 or 5 dB. You get down to 6 dB or so being the required signal-to-noise ratio to get a good bit error rate. Then the other is that, and this may be what Syntec is claiming, that's typically the case for the numbers like minus 140, is that you're lowering the data rate. You can't arbitrarily lower the data rate in most receivers because you can't get the filtering narrow beyond a certain point. I mean, even a crystal filter at RF frequencies is seldom below about 200 hertz bandwidth for the IF.
I thought there were direct conversion inside the chip. There's no coming out of the chip to a filter and going back in.
Yeah, but the problem with even direct conversion, where you can get very low bandwidth at baseband, is that you got phase noise on the oscillator that does the converting. And that phase noise, I'll show a graph of it later, is coming up as frequency comes down. And so you reach a point where you become phase noise limited in sensitivity.
Jitter on your
Right,
oscillator.
and that sets a lower limit on how low you can take the data rate or the bandwidth.
So it looks great on the data sheet, but maybe doesn't get you the link budget you think you're getting.
Well, they may be telling the truth because there's a way out of this trap.
Yeah.
And the way is to use direct sequence spread spectrum and chip up to a
Chips.
higher data rate that you use a wider filter, but then you kind of get this artificial noise bandwidth narrowing due to what they call the processing gain of the direct sequence. So it sounds real fancy, but basically it's just a way to get ultra narrow bandwidth. And there's a couple of chips out on the market that do this, and if you can get data rates of like 100 bits per second and noise bandwidths of 100 bits per second. Then you drop a 6 dB received noise figure on top of that, and you're at about the limit of physics. Okay, so I kind of covered this. I can go a little more detail about what's so nice about frequency synthesis, but basically you get any frequency you want with crystal accuracy. And when you're getting it, you get VCOs that are noisy, and side effect of synthesizers is that within their noise bandwidth they will suppress the noise of a VCO because it's a feedback control system, and if it sees frequency variation, noise is frequency variation, it's going to counter that. And these days you can get them in a single chip. And they may be noisy, maybe a noisy VCO, but that thing I'm talking about suppressing inside the noise bandwidth allows that to work. So here's a block diagram of a frequency synthesizer. You've got a crystal oscillator. You may divide, say this is 10 megahertz. You may divide this down to, say, 100 kilohertz and have 100 kilohertz steps. You got a phase detector for comparing that reference frequency to the divided VCO frequency. You take that output signal, filter it, and that becomes what we call a steering voltage to the VCO. Now, this is no different than any other basic control system you've seen, with one intuitive problem you got to kind of overcome, which is that they treat phase and frequency as small signal variables. So just, you're used to thinking of voltage and current as small signal variables, but in a phase lock loop, it is phase that is the primary small signal variable. Okay, and here's an example of synthesizer noise. Say, you can predict what this noise is using an equation called Leeson's equation, and if you put all the terms in, you get within 1 or 2 dB accuracy on predicting this noise. Its character is that at, if I can get a pointer here, at far out frequencies you'll get down to the thermal floor, and then as you come inside the bandwidth of the resonator, it starts rising, and it keeps rising right up to 0 dB. And far out frequencies is rising at 20 dB per decade. As you get a little closer in and start seeing flicker noise in the active components in the VCO, it'll generally transition to 30 dB per decade. And you can predict this noise if you know how. And then once you put it in the loop, you will get some changes, like for good quality VCOs, the resistors in the loop filter generate enough noise that you'll see them. If you have 1K ohm resistors, that is enough thermal noise in a 1K to degrade a high quality VCO. Noise on the power supply will come through as well, because both the power supply and the input noise modulate the VCO, and that modulation shows up as phase noise. But inside this is one of the great breakthroughs in integrated radios these days. Inside the loop bandwidth, we generally see this little rise above the free running phase noise, which is due to the fact that the phase margin in that loop is less than 90 degrees. As we get into loop bandwidth, it starts suppressing that phase noise. Now, in a lot of modern integrated synthesizers, you have pretty poor Q on the die, and you get poor phase noise as a consequence, because according to Leeson's equation, phase noise goes down with Q squared. And with this lousy Q, integrated VCOs are typically noisy, but with what we call a modern fractional lens synthesizer, you can have loop bandwidths of hundreds of kilohertz or even over a megahertz, and then inside the loop bandwidth you will suppress this noise down to the multiplied crystal oscillator noise. And that's the basic trick that allows pretty good quality synthesizers to be fully integrated. Well, of course, everything in electronics is tending to get more integrated for the simple reason that it costs 3 cents a square millimeter to get, a wafer, and you can put a lot in a square millimeter of wafer these days. So simple economics drives everything to be integrated. For a long time, this was a problem for radios because you couldn't get high Q on that die. This has been, somewhat overcome with the wideband fractional end synthesizers that let you suppress that lousy noise down to usable levels, and then with the development of a lot of other specialized techniques like low IF and direct conversion. So these days you can get, pretty good radios, not the very best, but good radios can be placed into fully integrated form. Key system design insights. I recall when I first got in the cellular business, which was in the early 90s, I thought I was a pretty good radio designer. I walked in the door, I knew the circuit design, but I rapidly found out that I just was a complete babe in the woods compared to these guys when it comes to system design. And that system design revolves around this concept. Dollars are proportional to bits per second per megahertz per meter squared. So everything in these modern wireless system designs is designed around getting more conversations per square meter for the megahertz the FCC gives you. When you maximize that metric, you've got the system design that lets you make the most money. Anything else gets filed away. But you got to do that with, high reliability, which is, a link budgeting and interference control question. This is about the only thing in this introductory presentation we're going to look at any of the real math on, because it's fairly simple and it's very important to grasp the basics of it. Okay, the link budget is this simple analysis that takes into account all the factors that govern how much received signal strength is available. That includes the transmit power, the antenna patterns, the frequency you're at, and to some degree the modulation mode and the bit error rate. I'd call, the power and the frequency the first order factors, and everything else kind of second order, though second order does add up. So, all my career in radio, people have been asking, how much range do you get? Well, you can't say exactly really, because it's a statistical phenomenon. Under what conditions and at what reliability?
That's an engineer response.
Well, I mean, if this just varied 2 to 1, you could ballpark it in the middle or something, but the variation's about 2 orders of magnitude. The first thing about the math is the effective aperture of the antenna. If you read some basic antenna books like Balanis, you get this equation about effective aperture. But basically, this is the area over which the antenna looks like it's gathering in the incident energy density and putting it out of its port. And the important thing is that it is inversely proportional to the square of frequency. So in general, the lowest frequency you can use, if the antenna is not too big for resonance issues, is the best. One of the things that was always kind of striking to people in short-range radio is that the public really adopted 2.4 gig because everybody thought 2400 megahertz is better than 900 megahertz because it's a bigger number. But the frequency aperture is much better at 900 if you can use it. It's about 10 dB better. So everything else being equal, you got 10 dB more link budget to stay at 900 instead of going up to 2.4. Now, this equation, the Friis transmission equation, the Friis transmission equation gives receive power as a function of the ratio of transmit power over all these variables. Again, you've dumped in effective aperture, so you get frequency squared in the denominator, and then these are your antenna gains, and this is range with an exponent. In free space, that exponent is 2. In practice, it's more like 3. Cellular design typically assumes 4 because cellular's got a lot of bouncing around in the city, and they typically want that system to actually work without a direct wave. They want it to be reliable just based on the bouncing. Okay, so here's running some simple calculations for 100 milliwatt sensor length, say, at 1200 bits per second at 900 megahertz. And we see that we've got a nice sensitivity at this low data rate of about minus 127, and where the received signal strength falls below sensitivity, and that received signal strength being a function of range in meters, that's our range. So for pessimistic, assuming 3.5 dB propagation factor and a 15 dB maximum fade due to relative orientation and bounce, multipath fade, then we got a range there of about 300 meters. If we're more optimistic with a propagation factor of 2.5 and only a 5 dB fade, that 300 meters has turned into about 18 kilometers. So, it just, what's your assumptions that you're going with? A lot of times I've heard people quote inverse square like we're in free space, and of course, except for satellite operations, that is never the truth. Okay, some basic RF CAD tools. You can get SPICE for free or close to it these days. Works fine up through a couple of gigahertz if you put in your proper models. The only real disadvantage of using SPICE is it often doesn't work directly with S parameters, though there's some versions that have, S parameters built in. I use a version called TINA commonly that, you can get for free from TI and get various versions of it up to $1,200 for full capability. The best thing I know of on the market with S parameters built in is Link 2, available from that website, appliedmicrowave.com. It's got various versions running about $500 to $1,800. Fine little program. It's a one-man shop, but the guy does a good job. You can do anything you need with S parameters with that program. Basic RF library. Here's some of my favorite books. Introduction to Radio Frequency Design by Wes Hayward. Old radio amateur. I've been reading his articles in QST since I was in junior high school, but very good introduction to RF circuit design. Microwave transistor amplifiers is an outstanding description of S parameter based design. Oscillator design and computer simulation, excellent oscillator design book. Randy Ree used to have a program he offered like Link 2 that was called Eagleware that he ended up selling to HP, which promptly jacked the price up from about $1,000 to $20,000. But that was a good program, and Randy's a guy who knows about oscillators. PLL Performance Simulation and Design by Dean Banerjee. He's an apps engineer at National, now TI. Best book on the market. There's a couple of classic books there like Gardner and another by Best on PLL design, but they're limited to what we call the second order normalized form. Dean's the first guy to come out with higher order synthesizer design principles, and also he's a phone call away. So, terrific guy. Analog and Digital Communication System Design is the best book I know of for like an introductory graduate level communication system class that's going to explain, basic modulation and so forth from a system engineer's perspective. And Wireless Comms Principles and Practice by Ted Rappaport is an older book now, but excellent at introducing cellular principles, modern wireless design. So you can see we had a lot of topics here that I just hit on. And if there's, potential future interest in some of these other topics, let Gary know, and we can devote an hour to any of these where there's enough interest to put together a short presentation on it. Okay, so, in conclusion, a lot of things in RF are counterintuitive until you get into studying them. And then, in fact, they are scientific. The warning I would give anybody that's working in a company that doesn't have RF specialists is be pretty careful, because management tends to view it as they view other electronics, which is easier to analyze and that they understand. And I have seen many millions of dollars thrown down the drain by companies going into RF projects where they just did not get the basics right. So that's a very common trend.